Okay, so what we're going to do this time is a little demo that shows you how to do a test of independence, also called a contingency table, with Chi Square, and how to calculate the effect size, either phi, which would be for 2 by 2 tables, or Kramer's V, which would be for any table larger than 2 by 2. It turns out that those equations actually, if you use Kramer's V, like you always get the same answer. So we'll just do the one equation and we'll call it phi slash Kramer's V, which is the same thing that programs like SPSS do. So this is one where there's not an automatic option to do this. So we need to understand how the math works and just kind of go through some of the processes. Luckily, it's not that difficult. So what you have here is a table that shows the observed frequencies for certain outcomes. Now I have two variables, the type of vehicle and sex. Type of vehicle takes three levels here, or categories: car, truck, and SUV. And then sex here takes two levels, men and women. And so in each of these cells, what you see is the number of people who chose a particular option. So 13 men chose a car, 22 men chose truck, 11 chose SUV, 27 females car, 18 women truck, 18 women, or excuse me, 33 women SUV. So the first thing we need to do is figure out what our expected values would be, because chi-square is the sum of the observed minus expected squared over the expected. So we're going to use this process here to try to figure out how to put together those expected values. To do this, the first thing we need to do is get some column and row totals and then get the grand total for the table. So what we're going to do is use the sum commands here, and we're going to get the column totals. So this is the total number of people, regardless of sex, who purchased a truck. Once we've done that, we can grab and drag and get this for all of them. We're going to get the row total here, which is the total number of men, regardless of the vehicle they chose. There you go. We can grab and drag, and then we just need to sum. And you can sum either of these because they should sum to the exact same number. If they don't, there was a mistake somewhere. So there you go. So our total sample, 124 cases observed, 46 men, 78 women, and broken down like this for the different vehicle types. So now we need to get our expected counts. So to do our expected counts, it's going to be a table that looks just like this that we need to fill in. So I'm going to copy this table over. I'm going to paste it. And what I'm going to do is clear out these values to calculate the expected values. So the expected values are going to be the row times the column divided by the sample size. And you're going to do that for each of these. The sample size will always be the same. The row and the column will change. So we expected about 15 guys to pick a car based on the breakdown of how many guys there are and how many cars were selected. So we're going to do this same kind of process for all of these. So row, and then we pick the appropriate column, and we divide by the total. And we pick appropriate row, divide appropriate column, and divide by the total. And when we sum these, a nice way to check and make sure you've done it correctly, you should get the exact same size in the row. So we should have assigned every one of the 46 men to some value here based on how they're expected to be broken up overall, right? So the 40-40-44 split is basically being applied here. So notice that these numbers are equal because that's what's expected here for the grand total. This one's a little higher because that's what's expected here. We'll do the same thing for the women, taking into account that there were more women. So we're going to do these values divided by the total. We're going to do these values divided by the total. And we're going to do these values divided by the total. When we sum across, we could have dragged down, but we'll just do this. We should get, oh, I misselected something. Hold on, what did I misselect? Oh, see, I made the mistake right here. I did B4. This should be B5, and this should be Gotta watch what you select. This should be E4, E4, B5. There's my 78. Watch what you choose. And this is why it can be useful to make sure that you are getting the right values and not misclicking something like I just did there. So here you go. You've got, again, notice you expect an equal number of truck and car owners because that's the way that it's broken down in total, and a few more SUVs. So if men and women have the same car preferences, right? You taking into account you had fewer men than women in this table, then the breakdown should be the same, where men and women both pick cars and trucks at this rate, right? So there's a lower number here, but only because there are fewer men, but the rate is the same. So now we can also double check ourselves. What we should get is when we sum down that all of these totals should match our previous table. So there you go. So now this is our expected counts, and these are our observed counts. So the way that we get a chi-square value is simply summing all of the observed minus expected. So that can sound like kind of a long process here. What you're going to do is you're going to take the sum, and you're going to take observed minus expected squared divided by expected, right? And we're going to do this for every one of those terms. So now we're going to add to that observe minus expected squared. Watch the keys. Squared divided by expected plus observed minus expected 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 squared divided by expected. So when we sum all of these values, mistype something here. What did I mistype? I need a parentheses here. There we go. You got to make sure you balance all your parentheses. And there you go. So this is our chi-square value. So every chi-square can be tested for significance. You can do this using a tool like GraphPad or directly in Excel using the chi-square right tail function. So if we were to look at this, we would have to take into account the degrees of freedom. And the way we calculate DF, so the degrees of freedom for a chi-square are the categories, so columns by rows, -1. So 3 minus 1 is 2, 1 minus 2 minus 1 is 1. So we end up with 2 degrees of freedom for this table. So then we can get the p-value for this chi-square if we use chi-square.dist, and we can use the right tail function. We get the chi-square with the degree of freedom, and we get a p-value of 0.01, which would be statistically significant. And so there we've calculated out all of these values. Now the last thing to do would be to get an effect size for this, which we can get phi Kramer's V. And phi or Kramer's V, we can use one equation to get both of these things. It is the square root of the chi-square value divided by, and then we're going to take the sample size and we're going to multiply it by the smaller of the DF terms, which the smaller of the DF terms here is 1, right? And when you do this, this will get you the right answer for either phi or Kramer's V. Because notice, if you have a 2 by 2 table, Your book will tell you phi is just divide by n without that extra df term. But if you have a 2 by 2 table, then you're going to multiply n by 1. For example, we're doing that here because the smaller is 2. And so it's as if that df term isn't there. So we can use this one equation to always get the correct value. And so here we get an effect size of 0.26, which is a pretty good effect size. And so this tells us that there are significant differences in the buying patterns between men and women for their vehicle type. And we can do some specific type of like binomial follow-up tests or whatnot. But for our class, what we're going to do is kind of take a look and compare the observed and the expected values to see where the differences exist. So basically what we see here is that women are more likely to buy an SUV than expected, um, and less likely to buy a truck. That's really the biggest difference. Car and those aren't very different. The real difference is here 7 fewer in truck and about 6 more in SUV. So the real difference here is that females were more likely to get an SUV and less likely to get the truck than expected. Looking at males, we see that males are more likely to get a truck and less likely to get an SUV. And again, not a huge difference in the car number. So the real pattern lies there. So basically, males are more likely than expected to purchase trucks and less likely than expected to purchase SUVs, whereas females are more likely than expected to purchase SUVs and less likely than expected to purchase trucks. And so that would be the process for computing a test of independence or a contingency table with using chi-square to test for significance in Excel.